This Unit 3.1 study focuses on three new quantities, in particular work, kinetic energy, and power. We haven't talked about power yet, but this lesson will help us segue from what we know about work and kinetic energy to an understanding, or at least an introduction, of power. So we know that work is a product of force and displacement. And we know kinetic energy is energy of motion that depends on the speed of an object. So this idea that work depends on force and displacement can be investigated by taking a look at the behavior of simple machines. So the idea here with a simple machine is you can accomplish work in one of two ways. You can have a large force with a small displacement, or you could possibly get the same amount of work done with a large displacement and a smaller force. So let's say, for example, the task at hand is to lift a 36 kilogram object 5 meters off the ground. So if we let g equal 10 meters per second squared, then we can say a 36 kilogram object weighs 360 newtons. Okay, so the work that would be done, the simplest way would just be to lift it straight up. To get beneath the box and apply some upward force. Now, if you want to lift the box at a constant speed, then the force you apply upward should match the weight of the block. If you want to accelerate it as you lift it, then your applied force is greater than. So we'll say this is the case of lifting it at constant speed. So the applied force is equal to the weight, which in this example is 360 newtons. And the displacement points straight upward. So if the force is a constant value, we can just say work is equal to F dot delta S. And in this case, it's the magnitude of the force times the magnitude of the displacement, and cosine of 0 degrees, because your force points in the same direction as delta S. Cosine of 0, of course, is just 1. So this is a very simple calculation. The work would be 360 newtons multiplied by 5 meters. That's the same thing, by the way, as 180 newtons times 10 meters, which is 1,800 joules. Just to illustrate that multiplying by 5 should always be mental math, right? It's the same thing as dividing by 2 and multiplying by 10, right? 5 is the same thing as 10 halves. So if you want to multiply something by 5, first multiply it by 10, and then take that value cut in half. So anyway, enough said. Okay, so that's one way to do it. Spend 1,800 joules of energy to lift it straight up. Let me offer another suggestion of how you could get the object 5 meters off the ground. You could use a type of simple machine known as an inclined plane. And with the inclined plane, it allows you to take the option of doing the same amount of work with a smaller amount of force. So that's what we said, right? There are a couple options. A large force coupled with a small displacement, or increase the displacement at the benefit of doing the work with a smaller amount of force. So if we take the block put it at the bottom of an incline, and give it a push. Then the amount of force we have to overcome is less than the full weight. Let's make a free body diagram. Normal force points this way, and the weight vector points straight down. If we make that a resolved free body diagram, then I think it's easy to show that if you want to slide the block up the incline at a constant speed, then you have to overcome just the component of gravity equal to mg sine theta. So this applied force right here, as long as it's equal to mg sine theta, the block slides at a constant speed. So mg sine theta is definitely a smaller amount of force than mg, and without a doubt, if the height is 5 meters, the distance that you're going to apply that force represents the hypotenuse of this right triangle, which would be a greater value. In fact, if we call this distance d, then we can see from this right triangle that h is equal to d sine theta, or in other words, d is equal to h over sine theta. So in the end, if we calculate the work done using the inclined plane, it's a smaller force. Instead of mg at a height of h, it's mg sine theta at a distance of d. But as we see, d is just the same thing as h divided by sine theta. And so in the end, the amount of work that you would do in using this inclined plane still comes out to be the same amount of work that would be done to lift the object straight up. A force of mg over a height h. So with the direct lift, work is mgh. By pushing it up an inclined plane, the value of work is mgh. But the force wasn't actually mg. It was the smaller value mg sine theta, and the distance wasn't actually h. It was the larger value of h divided by sine theta. And keep in mind, this is assuming that it's a frictionless inclined plane. If there was friction, then there'd be a second force back in this direction down the incline, and so your applied force would have to be that much greater in the forward direction, and you would actually end up doing more work by using the inclined plane. So I suppose what we're talking about here is something known as an ideal simple machine. And ideal machines don't cause you to have to do extra work due to forces such as friction, right? An ideal machine has no resistive force, or no internal resistive force. What would be another option to lift this thing 5 meters? Oh, how about we hang a couple of tandem pulleys off the ceiling and then take another tandem pulley arrangement and attach that to the block that we're trying to lift. And then we take a rope, wrap it around the upper pulley, down through the bottom pulley, back up to another one of the upper pulleys, back down to the bottom pulley, wrap it up here one more time, and anchor it off to the top set of tandem pulleys. This is entirely possible. Now, instead of lifting the object from below, you can pull on this rope, and what's going to happen? As this one segment of rope gets longer, 1, 2, 3, 4 segments of rope are going to get shorter here. So if you were to pull, for example, a total of 20 meters of rope through your hands, then the distance this block would lift would be the 5 meters that we're trying to lift it to get the same amount of work done as the inclined plane or the direct lift from beneath. So a pulley system is a second example of a type of simple machine. If it's an ideal machine, the work input and the work output will be equal. In other words, you're going to pull with something that we'll call your effort force, and then there's a resistive force that you're overcoming. Now that's just equal to the weight of the block. There's also an effort distance. If you pull 20 meters, then the rope, 20 meters of rope is going to pass through your hands as you pull. We'll call that the effort distance. And of course, the object is going to lift a shorter length or shorter distance off the ground. Obviously, this is not made of magic rope. You can't have 20 meters pass through your hand here and get longer and not have the rope in all of these segments account for that same 20 meters. Since it's 4 pieces of rope, each one is going to get 5 meters shorter. So this would be the distance through which the resistive force is moving. So the work input is your effort force multiplied by the effort distance, and the work output is the resistive force multiplied by the resistive distance. Okay, so I guess what we're really trying to say here is let's make it a small effort force and a big effort distance so that we can overcome a large resistive force that's moving a smaller distance. In the end, it's the same amount of work. It's just that the work is done using a smaller amount of force over a larger distance. That's the trade-off with all simple machines. And because of that, if the distance is longer, then it's probably going to take more time to lift the object using the pulley system. To pull 20 meters of rope through your hand is going to extend the time that it takes in comparison to the time it would take just to get beneath this object and directly lift it straight over your head. Of course, to do so, you might have to be more powerful. So let's make sure we're clear on how we define power. Power is not equal to work. Power is not the same thing as force. Power is not the same thing as energy. It's a totally different quantity. Now, it relates to those other quantities. Power is related to work. In fact, power is equal to work divided by time. It's the rate at which work is done. And therefore, it's the rate of change of energy. Because after all, work always produces some change in energy. Okay, so we can write this as an equation. Power is equal to W over T. All right. Actually, I believe this would just be how to calculate average power output. If you want an instantaneous power output, then we have to divide some small amount of work being done in an infinitesimally small amount of time, right? By the way, we can write this another way and say instantaneous power is equal to, let's see, a small incremental amount of work would be an instantaneous value of force multiplied over a small incremental displacement. So we've just substituted FdS in place of dW. But this in turn can be thought of it as an instantaneous value of force multiplied by ds dt. But what is ds dt? Right, that's just a way of stating instantaneous velocity. So if you take the dot product of instantaneous velocity, oops, this is really a dot product of instantaneous force and displacement. So if you take the dot product of instantaneous force and instantaneous velocity, this is a way to calculate instantaneous power output. So average power output and instantaneous power output. This is sort of like average velocity versus instantaneous velocity, if you remember our study going all the way back to our first unit on kinematics. So this is the idea of simple machines. They don't allow you to do less work, right? We can make an example problem out of this. What is the purpose of simple machines? A, to do less work. B, to do the same work with a smaller force. C, to do the same work with less power. It turns out both B and C would be correct answers. Okay, so in the next video segment, I'll show you some examples of demonstrations involving simple machines.